Good morning, class. For our session today in General Physics 1, we are going to study scalar and vector quantities. These are the objectives of our lesson. First is differentiate vector and scalar quantities. Second, perform addition of vectors. Third, rewrite a vector in component form. What are scalar and vector quantities? Okay. For example, a measurement consists of a magnitude or nominal value and a unit. For example, 40.0 kilogram. 40.0 is the magnitude and kilogram is the unit. The magnitude describes how large is the measurement. And of course, you have the unit to indicate the kind of measurement that we have. So, because this is kilogram, so it means it's all about the mass. There are also measurements or quantities that can be completely described using directions. For example, 120 kilometer per hour is. So you have 120 as the magnitude, kilometer per hour as the unit, and is as the direction. In fact, this is what we call velocity, speed with direction. Okay? So from these examples, we can differentiate the two kinds of quantity. The first one has no direction. The second one has direction. So in the example of 40.0 kilogram, it is classified as a scalar quantity. Scalar quantities are quantities that can be described using magnitude only. In the second example, 120 kilometer per hour is, it is classified as a vector quantity. Vector quantities are quantities that can be described using both magnitude and direction. What are examples of scalar and vector quantities, or more examples of these two kinds of quantities? So let's have scalar quantities first. Examples are mass, time, temperature, density, volume, and speed. These quantities does not include direction. They can be completely described using magnitude only. Of course, you always have the unit in our measurement. So, for example, in mass, you have 500 grams, 120 pounds. For time, 1 hour, 20 seconds. Temperature, 37 degrees Celsius, 98 degrees Fahrenheit. Density, 120 grams per milliliter. Volume, 1.5 liters. Speed, 25 meter per second. What are examples of vector quantities? Remember, vector quantities have direction. They are incomplete if we do not include the direction. Vector quantities are the following: velocity, force, momentum, and electric current. So for example, velocity, you have 25 meter per second northwest. Force, 50 newton to the right. Momentum, 60 kilogram meter per second to the left. Electric current, 40 amperes to the right. So they always have a direction. And actually, there are more examples. And we will encounter every these two kinds of quantities, scalar and vector, as we study our course in physics. So I hope the difference between scalar and quantities is now clear to you. How do we add scalar and vector quantities? In adding scalar quantities, it is quite easy. You simply get the algebraic sum. For example, you want to get the total mass, 40 kilogram plus 20 kilogram. So you just add, you have 60 kilogram. In volume or liters, 1.5 liter plus zero point 0.5 liter is equal to 2.0 liters. So we just add. Okay? How do we get the sum of two or more vectors? In adding two or more vectors, this is more complicated because we have to consider the direction of each vector. For example, in a tug of war, group 1 exerts a force of 400 Newton to the left, while the opposing group 2 exerts a force of 410 Newton to the right. What is the sum of the two vectors? Which group wins the tug of war? So in this situation, you have force, and we know that force is a vector quantity. It has direction. In the tug of war, the two forces are in opposite direction. You have to the left and to the right. So for the forces exerted by group 1 and group 2. So how do we get the sum of these two vectors? Okay, so we have a picture here. So the two groups are playing tug of war, pulling the rope in opposite directions. The first group exert a force of 400 newtons in total. The second group exerts a force of 410 newtons in total. How do we get the sum of the two vectors? So what will be the sum or resultant of the two vectors? Which group wins the tug of war? In order to analyze the situation easier, we can draw a free body diagram or FBD. So what is a free body diagram? It is a diagram showing the chosen body by itself, free of its surroundings, with vectors drawn to show the magnitudes and directions of all the forces applied to the body by the various other bodies that interact with it. So in our example of two groups playing tug of war, we can represent the rope as a dot. So the rope is the object being pulled by the two opposite groups. So we can represent it as a dot, and the force exerted by the two groups are represented by an arrow. So for group 1, for 400 newtons to the left, so you have an arrow towards the left. And for group 2, 410 newtons to the right, so you have an arrow pointing to the right. So this is our free body diagram for this situation. Okay, so uh, free body diagrams makes us easy to analyze the problem. Okay, when we represent vectors graphically using arrows, the head of the arrow points to the direction of the vector. The length of the arrow should be proportional to the magnitude of the vector. In order to achieve this, we can use a scale. So I mentioned earlier that we use a free-body diagram in order to analyze the problem easily. So we can just draw arrows to represent the forces acting on the body. Okay? In addition to that, In order to get the sum of the two vectors easier, we can represent the vectors using arrows, and then we also specify the length of the arrow. So the length of the arrow should be proportional to the magnitude of the vector. Okay? And how can we make that accurate? We can use a scale. So for example, we can use the scale 1 centimeter is to 100 newtons. Okay? So if our two vectors, 400 newton to the left and 410 newton to the right, we can represent them graphically uh, through this diagram, okay, shown in this diagram. So you have the 400 newton to the left, and we add 410 newton to the right. What will be the resultant or the sum of these two vectors? So we draw the two vectors using put rule or ruler. Sorry. So using the put rule, we use the scale 1 centimeter is to 400 newton. So the first vector, 400 newton to the left. So we draw a line 4 centimeter in length. So in every 1 centimeter, it is equivalent to 100 newton. And then we also put segments here, so we can uh, see the the measurement. So you have four segments representing 100 newtons each. So you can say this is 400 newton. For the second vector, we apply the same process also using the put rule. For every centimeter, equivalent to 100 newton. So you have four segments. The first three segments are 100 newtons each, and the last segment is equivalent to 110 newton. So that the total is 410 newton. As you can see, the segment um, at the front of the arrow, or fronting the arrow, is quite longer, meaning it is 100 newton, or 1 centimeter plus zero point 0.1 centimeter, representing the additional 10 newton. So so it will look like the arrow for the second vector is longer than the arrow compared uh, the first vector. Okay? And if we take the difference between the two arrows, you get this small one. And that is equivalent to 1 centimeter, zero point 0.1 centimeter, or 10 newtons. And the direction will be to the right. Okay? So this is actually graphical method of getting the sum of two or more vectors. Okay? So we use the graphical method to get the sum. Alternatively, um, we can also use algebra. Okay? Remember, in the adding scalar quantities, it's just algebra. You just add, and that's the sum. In adding vectors, we can also use algebra um, sometimes. Okay? Not all the time. So in this example, you have 400 newtons to the left. So that will be negative 400 newton. And 410 newtons to the right. So that will be positive 410 newton. So when you add them, you will get 10 newton as the sum of the two vectors. Okay? Okay. So that's how you add two or more vector quantities. Okay? So it becomes more complicated because vectors have directions. We cannot simply use algebra in adding them. We have to consider the direction. Okay? So, what if the two vectors are of the same direction? Okay? So, in the first example, tug of war, the vectors or the forces are opposite in direction. How about if they are the same direction? So, for example, you have student A pushes the cart with a force of 7 Newton, and student B pulls the cart with a force of 9 Newton. What is the sum of the two vectors? Okay, so in this situation, the two forces are in the same direction. Okay, so using our graphical method, so we represent the vector using graphs or arrows. So in our pre-diagram and graphical method, you have the cart represented by a dot or a small circle. Um, Student A pushes the arrow 7 Newton to the right. So this is her vector. Our scale is 1 centimeter is to 1 Newton. So for every centimeter, equivalent to 1 Newton. Student B pulls the cart 9 Newton to the right also. So this is his vector measuring 9 centimeter. Okay? So since 9 Newton is the force exerted by student B, then that will be 9 centimeter of arrow represented graphically. And it is longer than the arrow of student A since 9 Newton is uh, larger than 7 Newton. So that's why it is important to use a scale, and the length of the arrow should be proportional to the magnitude of the vector. Okay? So since the two vectors have the same direction, we can simply add them. Okay? 7 Newton plus 9 Newton will be equal to 16 newtons to the right. Okay? So, um, so the first two examples, okay, they are quite simple. Okay? So the first example, the two forces are opposite in direction, so magka-cancel lang sila. Okay, yung opposite direction negative, yung another direction positive. So magka-cancel lang sila. Dito naman sa second example, um, same direction, so mag-a-add lang sila. Okay? And we will encounter more complicated situations, okay? Uh, in adding vectors. Now, going back to our second example, you have two forces in the same direction. And this is the pre-body diagram, right? Okay. Now, how do we represent the sum or the resultant vector of these two vectors? So when you say resultant, it also means the sum. Okay? Or pag pinagsama, anong magiging resulta? Okay? That's why we call it resultant. So pag pinagsama natin yung dalawa o higit pang vector, meron silang resultant vector o yung vector na equivalent kapag pinagsama sila. Okay? So, yun yung ibig sabihin ng resultant. Okay. So, how do we draw the pre-body diagram for the resultant vector in our previous example? So, let me uh, draw in my Jamboard. Okay, so I hope you can see the Jamboard. Okay, so I have the Jamboard now. So in our second example, you have our first vectors. Okay, by the way, class, we can symbolize a vector. How do we symbolize a vector? So for example, you have in our previous example, the force, sorry, ay, uh, the force exerted by student A is 7 Newton. She is pushing the cart 7 newtons to the right. And the force exerted by student B is 9 Newton to the right also. So we use F as the symbol for force. And we can put an arrow on top to show that the the quantity is a vector quantity. Okay? So that's how we symbolize vector quantities. We put an arrow on top. Okay? So kapag scalar, walang arrow sa taas. Kapag vector, we put an arrow on top. Okay? So that's how we represent the vector. So halimbawa, um, kapag acceleration naman, ganun din. Vector quantity and acceleration, so may arrow siya. Or sometimes, para mas mabilis, ganito yung ginagawa, ganun na lang. Pag velocity, small v, ganun din. Okay? To indicate that it is a vector quantity. Okay? Okay. So going back to our example, in our free body diagram, uh, the cart is represented by the dot. So the first student A, 7 Newton. Okay? So we draw it proportionally. Okay? And the student B, 9 Newton. So when you add the two vectors, magiging 16 Newton to the right, di ba? So the resulting free body diagram for this will be like this. 16 Newton. Okay? So we also draw it proportionally using a scale. Okay? So of course I cannot do it with the Jamboard. Okay? But if we use pen and paper or graphing paper and pen, uh, we should draw it proportionally. So this will be the resultant vector. Okay? The resultant 16 Newton to the right. Okay? So um, the two students pushing and pulling the cart to the right exert separate forces It is also equivalent to a single person pushing the cart 16 newton to the right. So equivalent sila. So let's say si student C ang gumawa nito. Student C, tinulak niya yung cart 16 newton to the right. Equivalent din yon nung per situation. Student A pushing 7 newton and student B pulling 7 newton to the right. Okay? So the two forces are equivalent. Okay? Now, uh, what if um, we have forces at an angle? Okay? So in our previous examples, you have horizontal forces only, di ba? To the right, to the left. What if our forces has an angle? Let's say this one. The force is inclined. So meron kang angle. Let's say 45 degree. Okay? Tapos, another force here. Okay, so first F1, F2. Pero along the x-axis naman. What if may force din dito pababa? Okay? And there's another force here also. But downward. Let's say 30 degree naman from the x-axis or horizontal. So this becomes more complicated, right? So in this case, we are going to use trigonometric functions. Okay? Uh, Sine, cosine, and tangent as well. Okay, so that will be for our next session. Okay, so I hope uh, you understand something from what I discussed. Please wait for uh, my next lecture.